Hello and welcome to Engineering Tower Room 141. This is basic electrical wiring soldering we're going to talk about this session. My name is Robert Smitty Smith. I'll be your instructor on this, and I'm going to show you some of the do's and don'ts of putting wires together with solder. So, if we look down on the table before us, I've laid out a few little of the basic tools we need when we solder wires together. You'll be doing projects and you're going to need to have a basic understanding of how to do this correctly. And let's look at the equipment. First of all, we have the basic soldering iron. This is a pencil type. Reason? Because you hold it like a pencil. Has a sharp tip. This is the heating element. It's got an insulated handle here. Has a cooling spring here and holder that it resides in. This one's been plugged in a while, so it's hot. And it has this nice little base, and so it parks there when not in use. A more sophisticated one will have a controller and be temperature controlled, but this is just a basic electronics 25-watt pencil type soldering iron. Notice here in the base you have a sponge. That's for cleaning the tip, because the flux in the solder will oxidize, turn black, and you have to keep the tip clean, keep all the crap cleaned off of it to get nice clean solder joints. This device is called a third hand, so if you don't have a helper to hold the wire for you while you're trying to manipulate the solder and the soldering iron, this will do it for you. Third hand, simple little device, only a few dollars. This is a higher powered pistol type soldering iron. This one's 25 watts. If you see on this one, if you can read it, is, let's see, it's a D550. Don't believe it says on this one, but anyway, this one is 250 and 325 watt. Has a 2-position trigger. And this one has 10 to 12 times the power of this one. Now let's talk about scale. If we're putting together wires this size, we use a small pencil type. This is your small electronic project type. If we have a ring terminal this size, this is the size you would use to hook up a battery to the electrical wiring harness. You'd have a great big heavy cable laid in here. You'd fold these ears over it and you'd want to solder it. You got to have a gun with some real power to heat this up. This little tool here would just sit there and hum all day long, but it would not get things hot enough to properly flow the solder. Solder has a certain melting point. It's a eutectic mixture. Eutectic's a wonderful word. As a mechanical engineer, you should know what that is. You should look that up. Okay, now the solder most often used is rosin core solder. It's usually about a 60-40% mixture of tin and lead. And it has rosin in the core inside the solder itself, which comes out as the solder melts, and it acts as a cleaning agent, protects the solder from oxidation, and helps it bond with the metals to be joined. Here's some from Radio Shack, very inexpensive. And the smaller the size solder, more scale to the work. You would use on this side wire. Let's see if I have some larger size. Yeah, here's some much larger size rosin core solder that would be used on this scale work. So you always want to scale your tools to the job at hand. Now, I'm going to use this little wire. Now, we have to remove the insulation from wires to get down to the metal core to solder them together, or to attach ring terminals. Ring terminals are these little devices here. It's got a ring on the end. It has a little insulating sleeve, and then it has a little formed tube here that the wire goes in, and then use a special pair of pliers to crush it down, and it's called a crimp type connector, or you can put the wire in and actually solder it to the ring terminal, which is a more secure way of doing it than the crimping. But irregardless, you have to strip back the insulation. And I'm going to show you how to do that correctly. Now, there are very nice stripping tools. Here's two. They're my personal ones. This one goes from 30 gauge wire down to 22. This one goes from 26 down to 16. That refers to the die sizes of the jaws here in the opening. But these are expensive tools. These are professional level tools. They're a good $25, $30 a piece. And often they won't be available when you're doing prototype work, you're working in a shop somewhere. These are more of a technician grade pliers. And most people aren't lucky enough usually to have pliers of this level. Here is some what's called auto strippers. They have the same dies here. They also have jaws that grab it, and they're spring loaded to actually grip, grab, and separate. You select the correct die size for the wire. Let's see. And ever how much you want stripped off, you let it extend, you squeeze and pull. Now, I didn't have the right die size. I was on the one next door. There we go. Perfectly clean. The dies close down around without overly nicking these individual strands inside and damaging them. Often on a very, very high quality job, you want to check with a magnifying glass to make sure that ever how you're stripping it is not damaging those wires, because pressure, vibration will cause that joint to fail later on if too many of those wires are damaged. Now, here is what's always available. Single edge razor blade. With a single edge razor blade, we're going to show you how to do it. We'll cut this back off so we don't have any extended. You can use it down on very small wire. You can use it on wire the size of my thumb. It's all the same process. It's a little slower than the professional level tools, but it works just as well because it works just like they do. Those dies close down a specific amount, slice into the insulation, and they do not gouge into the multi-strand metal core. So here's how you do it. You take a straight edge laser blade, you lay your wire down where it's backed up, you figure out how far you need to strip it back. And to do that, you need something to gauge it by. Now, on a ring terminal, we want that wire to stick out past the end of that little tunnel there. Now, the first of the tunnel is just plastic. The metal part that actually holds on to the metal core is this long, so we need that length plus a little. So if we hold it right there, and we need to strip it back to about right there where my thumbnail is. So I generally lay it down, place the blade right there, and then gently, mind you, with very little pressure, just roll the wire. And just with a little pressure, the single edge razor blade will slice down through the insulation and not overly gouge. And if you do it right, you can pull it off with your hand. Now, if you've got individual strands that break and fall away, you put on too much pressure. It's very, very light pressure. You don't need a lot. So there we have it exposed. If we insert it into the ring terminal, the first part of the ring terminal is just to accommodate the insulation. And there we go. See the extension? That's just right. If we wanted, now we could crimp this with crimping pliers, or we could solder that wire to that ring terminal. Crimping is okay. It works quite well for many, many applications. However, soldering is always better. Now, that's how you do that. Now, I'm going to show you, most of the time, what gives most people the most problems is trying to create a butt joint with solder. So we're going to strip this little 20 gauge wire back. Let me find something that goes down to 20. See, those pliers don't have the right jaws. Yep, these do. Let's strip these back now. Because we're going to mechanically overlap these little darlings, we want a little bit extra. We can always trim it off. See, these pliers just nip down. Now, we have exposed, and if it sort of frays out, you want to grab it and twist twist it back a little bit to keep having a bad hair day with individual strands. Just twist them back a little bit. Now, we want to get these little devils together. Now, a lot of people, this is where the third hand is handy. A lot of people try to solder these together like this, just lap them. And if you've got someone to help you, or you've got a third hand, you can do that. And we could solder that. But a superior way to do it, strength-wise, is to cross them and then just ever so slightly twist. If you can do this, you increase the surface area and you will increase the quality of the joint immensely than if it's just simple. And also it can be a slimmer joint. And see, it pulls apart. It just one side curls around the other. Now, when we finish this, we have to insulate it. So this is what's called heat shrink tubing. It's flexible plastic, thermal sensitive plastic. We put that on there because we don't want to tape it afterwards. Taping is a very crude way to insulate wires. It should be used for emergency use only. It shouldn't be anything that's semi-permanent. It should be only the most temporary of repairs. We'll use our little third hand to hold this so you guys can see what I'm doing, okay? So I've sort of twisted it together. I've already got my heat shrink slid on. We're going to take our little pencil-type soldering iron because it scales just perfectly for this. We look at it, we see that the tip is sort of dark gray and everything. It's been sitting there hot. Now this is a dampened sponge, and as we drag across it, it will wipe off. See how much shinier it is now? It's getting off all that oxidation. The oxidation will contaminate the solder joint. Also, if your solder has been lying around a long time, I had a little knot in it there. Let me get that knot out so I can pull out more. That happens sometimes when these dispensers, you sort of knots internally. It's not a bad idea to wipe this off too if it's been lying around in the shop dirty. Okay, now I'm going to show you what not to do. This is what most beginners do. They have the gun, the pencil soldering iron, and they're trying not to burn themselves because this end is hot. It's hundreds and hundreds of degrees. This stuff melts at about 375 degrees, so the tip has to be hotter than that. That tip's probably 450 degrees. It'll bring a blister on you instantly. So you're trying to stay away from that, and so you get it up here, and you know you got to heat that wire up, and then you got to stick the solder, and it's all wandering around on you. So generally, this is sort of what happens, is that you stick, the gun is just sort of touching and not touching, and you're sticking. You stick the solder here, nothing happens. So you stick it over here to the tip of the gun, and you wind up dripping it off, sort of like candle wax, and you call that good. You can't drip it off like candle wax. Even if you get a little bond, it's not a really good bond. As you can see on the other side, it's as dry as the Mojave Ocean. Okay? See that, how there's no solder? It's just got a little bit that bonded right on top. If you put this in a severe application with a lot of mechanical pull, a lot of mechanical vibration, or you send a lot of the maximum amount of electrical power down these wires, that joint can fail. Now let's go back and do it correctly. Let's re-clean our tip because I left a whole ugly booger of solder on there. Now I'm going to put a little bit on the tip. This is called tinning. Now what I like to do if I have the room, I always put the hot tip underneath for two reasons. One, heat rises, okay? Two, we want the wire to be hot enough on its own to melt the solder. See that? I'm nowhere near that tip. I'm way over here. Now, that's a properly soldered joint. Another good point to make is that we always want the soldering iron to have enough energy to be large enough so it quickly heats things up. If you have a big wire and a small soldering iron and you have to sit there and heat and heat and heat, well, copper is a great conductor. it's conducting heat all the way down and around. Eventually, this insulation can melt just because you sit there for 5 minutes trying to heat it up. And it's not to the point of melting the solder, but it's to the point of melting the insulation. So you want enough energy to heat it up fast and then cool it. Now when we turn this over, can your camera see that? We have solder has flowed all the way around. That is a completely solid joint. If we pulled on it, and I'm pulling, will not slip, will not come loose. Chances are the wire will break somewhere else, it will not break there. Now we need to insulate it. Slip our little heat shrink tube in. If you've never used heat shrink before, it's great. You want to put it, locate the center of that, put the center of the heat shrink over it like that. It's heat sensitive. I have a heat gun right here. Now, if you watch it, it's going to start shrinking from the heat of the hot air gun. This is like a souped up hair dryer. Now I'm going to turn it around so I make sure that the hot air, you can actually see the form of the solder underneath. And you don't want to sit and just keep shrinking it. You just want to bring it down until it conforms to what's underneath. And it'll still be a little warm. Don't grab it right away. But if it's shrunk properly, it will adhere to where it will not slide. That's very important. If it slips off, it could expose the bare wires, which could create a short. Not a good idea. Okay? So there you go. There's a properly spliced butt joint with heat shrink insulation. This heat shrink can actually add reinforcement. I want to show you what a good job looks like. Let me find some little show and tell goodies here. Okay, here's a three-way switch. And on the back side, you can see the jumpers, which jump from one side of the switch to the other. You notice they're in nice little neat loops. Notice the heat shrink goes all the way down to the base of the blade coming out of the back of the switch. And all of these have been soldered properly. The heat shrink was moved down. What this does, the heat shrink not only protects against shorting, it acts as a reinforcement to the solder joint. This wire could sit here. There's a lot of vibration in airplanes, race cars, bulldozers, all kind of industrial machinery. They vibrate enormously. It's hard to imagine how much vibration going on. But with this added reinforcement, this is a nice, strong, clean, neat system. Doesn't have excessively large jumper loops. They're not excessively short. They're comfortable. They're nothing stressed. Everything is as it should be. That's a first-class job. This was actually on a control switch for a nitrous system on one of my play toys that I had a few years back. And once you can solder, you can do lots of interesting tricks. Speaking of nitrous, here was a micro switch on the throttle. That throttle went wide open, allowed continuity, nitrous turned on. However, I found out there was a problem on one particular vehicle that we had. If the RPM was too low, RPM needs to be about 60% toward red line before nitrous turns on. And if you've got a vehicle that has a really wide power band, sometimes you turn the nitrous on full throttle a little bit before. At low RPM, the nitrous flows at a continuous rate, but the engine RPM is slow. So the nitrous builds up in the intake, and when the cylinders inhale, they can inhale a disproportionately large amount of nitrous oxide, and they can become overboosted and detonate and do all sorts of things like that. So if you want a reliable system, it's best not to turn the nitrous on until you're at a certain RPM where the engine's spinning fast enough so that the time window involved only allows the cylinders to inhale the calibrated amount. So, shift light. I used a simple $50 shift light. Here's a bulb that went bad in a shift light. Like I say, race cars vibrate a lot. They shook the shift light bulbs to pieces on a regular basis. But the shift light was quite reliable, so I was thinking to myself, how could I simply safety the system so that I wouldn't over nitrous the motor below a certain RPM. And I said, oh, shift light adjustable. So I changed the pill in the shift light to about 60% of what the engine would turn at redline. And I took one of these old blown bulbs, broke the glass off of it, soldered on 2 lead wires to the filaments that came out the bottom, ran this in series with the micro switch on the throttle. So now shift light had to be turned on before the nitrous system would flow nitrous. So when the RPM came up above 4,000, shift light turned on. If the throttle was open, nitrous flowed. Made a totally reliable system. That engine took hundreds of shots of nitrous, no harm, no foul, once we sorted out the issues. So nice little tricks you can do. Notice again, the heat shrink here is extra long here again to provide reinforcement. Now, one thing I do recommend staying away from in automotive applications, and they're very, very common. These are the clamp-on type connectors that are very, very popular for wiring up trailers, wiring up stereos, and basically the way they work is that I'm going to open this up and see if the camera can zoom in. These are blades with a V that actually go down, pierce through the insulation, and they actually, because they're on a V, they actually bite in to the copper strands and they weaken them. They have this little strain relief to keep from pulling on them, but I just don't like these type of connectors because they actually slice through some of the strands and can weaken the joint severely. But they're very common, they're very popular, and for a non-super duty use, they get by okay. But I would much prefer something like our soldered joints than something like this. And you will be doing a lot of butt connectors because, like, here's a simple inline fuse that you would want to put in, and you would want to use this kind of butt connection to do it. If you could do a simple twist, put it together, and then you're fine. Let's see if we can find anything else we want to discuss here. I think that's pretty much it. Let's see. Here in an unopened pack is a relay. Now, you see, these are blade type connectors. This is a blade type connector. This is a male, those are male, and then they make female type connectors that go on. But you notice they have a hole. Guess what that hole's for? That hole is so you can strip back wire, stick it through the hole, lay it down, and solder it to the blade. Then slide some heat shrink down. That's going to be better than something that just pushes on and sits there. So if you've got a super heavy duty application that's going to vibrate, it's going to be tortured, solder your joints, all of them. Don't trust blade type connectors, and don't trust pierce type connectors. They will get you into nothing but trouble. And I know what I was looking for. I was looking for this. This is a nut type connector. This is used in house wiring, and I'm going to show you how it works. Take this, put it back on itself. This is the way in these buildings and all these wall plugs, this is generally how the wires are put together. The wires are twisted around one another. There's a conical shape on the inside, just like on the outside, and there's threads on that plastic. So what you do is you just rotate it, and it will just screw itself down and hold the wires. That's called a wire nut. Do not use these in automotive applications, except in just a have-to situation. Why? Because if it screws on, it can screw off. Okay? Now, inside a wall plug, when's the last time you saw a wall plug vibrating around like that? Okay? In a static installation, they're fine. They're wonderful, like inside your wall of your house. But under the hood of your race car, in the trunk, something like that, they're not good at all. Stay away from them. Don't even think about it. Okay, so that's basic soldering and wiring 101. Remember, add heat to the wire. Let the hot wire melt the solder. Then the solder will flow. Do not stick wire to the tip of the soldering gun and drip it off like candle wax and let it just sort of gob up. That will always give you an inferior joint. And try to put it underneath and let heat rise. And that's the secret to it. Let the work melt the solder, not the gun. The gun or the soldering iron heats the wire or the connector. Then the hot connector melts the solder. You do that, it'll work. And that's it. Basic soldering. Go do your projects.